Resources evaluation and needs, sizing of integration renewable systems. Evaluating resources and sizing integration for renewable energy systems is a crucial step in designing an effective and efficient renewable energy project. Here are some steps to consider. Resource evaluation. Solar energy. Assess the solar irradiance in the region where the solar panels will be installed. Tools like NASA's Surface Meteorology and Solar Energy Dataset, SSE, or online solar irradiance databases can provide valuable information. Wind energy. Measure wind speeds and directions at the proposed installation site. Historical wind data from local meteorological stations or online databases can be used to estimate the average wind resource. Hydropower. Evaluate the water flow rate and the head, vertical distance, available for hydropower installations. Stream flow data from relevant authorities or hydrological studies can be utilized. Biomass energy. Analyze the availability of biomass feedstocks such as agricultural residues, forestry waste, or organic waste generated by industries or households. Geothermal energy. Conduct geological surveys and exploratory drilling to assess the potential for geothermal resources in the area. Energy needs assessment. Analyze the energy demand in the target location. Consider current and future energy needs, including seasonal variations and trends. Identify the types of energy required, electricity, heating, cooling, and their respective load profiles, patterns of energy consumption over time. System sizing. Based on the resource evaluation and energy needs, size the renewable energy system to match the demand appropriately. Oversizing or undersizing the system can lead to inefficiencies and increased costs. For solar and wind energy systems, use the capacity factor, average actual power output over time divided by the maximum potential output, to determine the appropriate size. For hydropower, consider the flow rate and head to estimate the potential power generation capacity. Sizing for biomass and geothermal systems will depend on the availability and energy content of the feedstocks or resources. Integration and storage. Assess the need for energy storage solutions to address fluctuations in renewable energy generation. Battery storage, pumped hydro storage, or other energy storage technologies can help balance supply and demand.
Interfacing requirements of renewable systems. Interfacing renewable systems involves connecting renewable energy sources and related equipment to the electrical grid or other energy systems. The goal is to ensure efficient, safe, and reliable integration of renewable energy into the existing infrastructure. Here are some key interfacing requirements for renewable systems. Grid compatibility. Renewable energy systems must be compatible with the existing electrical grid to ensure smooth power flow and prevent disruptions. Grid codes and regulations dictate the technical specifications and performance criteria for connecting to the grid. The system must meet voltage, frequency, and power quality standards set by the grid operator. Power electronics and inverters. Most renewable energy sources, such as solar panels and wind turbines, generate direct current, DC, electricity. However, the grid operates on alternating current, AC. Power electronics, like inverters, are required to convert the DC power from renewables into AC power suitable for the grid. Synchronization and phase alignment. For grid-connected systems, the renewable energy sources must be synchronized with the grid's AC frequency and phase. This ensures that the power generated by renewable sources is in phase with the grid power, avoiding instability and blackouts. Grid protection and control. Renewable systems should have protective devices to isolate them from the grid during faults or disturbances. Additionally, they should have control capabilities to regulate the power output and response to grid requirements. Smart grid integration. Implementing smart grid technologies can enhance the integration of renewables. Smart grid features, such as advanced metering, demand response, and energy storage integration, can optimize the use of renewable energy and improve grid stability. Energy storage integration. Renewable energy sources are often intermittent, which means they don't provide a constant power output. Integrating energy storage systems, like batteries, can help store excess energy and release it during periods of low renewable generation, ensuring a steady power supply. Communication protocols. Renewable systems need to communicate with the grid operator and other components in the system. Standardized communication protocols, such as Modbus or IEC 61850, facilitate data exchange and system control. Safety and compliance. Interfacing requirements also encompass safety considerations.
Voltage control in smart grid. Voltage control is crucial for maintaining voltage levels within acceptable limits to ensure proper functioning of electrical equipment and prevent damage to the power system. In traditional power systems, voltage control is primarily achieved through automatic voltage regulators, AVRs, installed at substations. In regs, voltage control becomes more complex due to the decentralized and intermittent nature of renewable sources. Some methods for voltage control in regs are: A. Reactive power control. Regs can contribute to voltage control by adjusting reactive power output. Wind turbines and solar inverters can be equipped with control mechanisms to regulate reactive power flow. B. Volt-var control. Utilizing volt-var control strategies can help regulate voltage levels by adjusting the reactive power output of renewable sources based on the voltage measurements at various points in the grid. C. Coordinated control. Integrating voltage control algorithms with load frequency control and energy storage management can provide a more comprehensive and efficient control approach. D. Smart inverters. The use of smart inverters in solar PV systems can enable advanced voltage control capabilities by allowing real-time communication and control. To achieve effective load frequency and voltage control in power systems with a high penetration of renewable energy, a combination of these methods, along with advanced control and communication technologies, is often necessary. Proper planning, coordination, and integration of renewable energy sources are vital for maintaining the stability and reliability of the grid. Load frequency control, LFC. In regs, load frequency control becomes more challenging due to the intermittent nature of renewable sources. Solar and wind power generation depends on weather conditions, and their output fluctuates. Various methods are employed. A. Energy storage systems. Integrating energy storage systems like batteries can help store excess energy during high generation periods and supply it during low generation periods, stabilizing the grid frequency. B. Advanced control algorithms. Implementing advanced control algorithms that predict renewable energy availability and demand can enable more proactive load frequency control. C. Demand response. Implementing demand response mechanisms can incentivize consumers to adjust their electricity consumption during peak and off-peak periods, helping to balance the load. Nonlinear controllers. Nonlinear controllers are designed based on nonlinear control theory, which allows for more complex relationships between the input and output. These controllers are employed in systems with highly nonlinear behavior or when the operating range extends beyond the capabilities of linear controllers. Nonlinear controllers often use advanced control techniques, such as adaptive control, fuzzy logic control, or model predictive control, MPC. These techniques can handle more complex and dynamic systems and may provide better performance in certain scenarios. A. Fuzzy logic controller, FLC. Fuzzy logic controllers use linguistic variables to represent the system's behavior. Instead of using precise mathematical models, FLC relies on human-like reasoning to make control decisions based on fuzzy rules. It is particularly useful when dealing with uncertain or imprecise information. B. Model predictive control, MPC. MPC uses a dynamic model of the system to predict its behavior over a future time horizon. It then optimizes a control sequence to achieve desired objectives, such as maximizing energy production or minimizing costs. MPC is effective in handling constraints and disturbances in renewable energy systems. C. Adaptive control. Adaptive control techniques adjust controller parameters in real time based on the system's changing characteristics. This approach is suitable for systems with uncertain or time-varying dynamics. In renewable energy generation systems, nonlinear controllers are often employed in complex and dynamic components like grid-tied inverters or energy storage systems, where the behavior is nonlinear and requires sophisticated control strategies. In summary, both linear and nonlinear controllers play essential roles in renewable energy generation systems. Linear controllers are commonly used in simple systems with relatively predictable behavior, while nonlinear controllers are employed in more complex systems that require advanced control techniques to achieve optimal performance. The choice of controller depends on the specific characteristics and requirements of the renewable energy system being controlled.